round 2 for today, and we are carrying on with the topic of light, and this is chapter 3.2.3 titled thin lenses. Right, so a lens is a device, so to speak, that causes refraction of light rays. Right, so it is a transparent object made of either glass or plastic that bends light. So usually made of glass or plastic that bends light, or in other words, causes refraction, right? And it has at least one curved surface. So you can find lenses in a variety of instruments such as cameras, right? Spectacles or eyeglasses, spectacles and telescopes, for example, and microscopes. So all of these things utilize lenses. Now, primarily there are two types of lenses. One is the converging lens.
And the other, can I guess?
Yeah.
Concave or convex?
No, those are alternative terms, or actually the more scientific terms for, right, the two types of. So converging lenses are convex lenses.
Okay.
So convex lenses are converging lenses. And so basically what happens, right, they look like this, something like that, right? And so you can see that they are curving outwards,
Yeah, and while the other, I think it's like an hourglass.
kind of, yes, right?
Okay.
And so the surface is curving outwards. And when you have, right, beams of light hitting it, passing through it, in fact, I shouldn't say hit, right? This one, we'll talk about this one in the center. It passes straight through. And then these guys bend,
To meet at one point.
right? And they converge at a single point.
Yeah.
Okay.
Yeah.
So what's happening is that light rays bend inwards. Okay. And they
Yeah.
converge at a certain point and converge at a point. Just to draw the arrows for the direction. Then the other guy that you have are diverging lenses, more formally known as concave lenses. And so what's happening with these, as you said, they sort of look like an hourglass, and so they are, let me just make it a bit broader so it's easier to illustrate. Like that. Okay.
Yeah.
And so similarly, for example, you've got this light ray coming in from the center, and so it's going to pass straight through. Then you got these other two light rays coming in, and because it's a diverging lens, what's going to happen is it's going to actually move away, so they're going to bend outwards,
Yeah.
right? And so you can see that the surface is curving inward. So the surface is curving inwards.
Wouldn't you stay outwards? Oh, okay. You mean that? Okay.
The surface of the lens
Yeah. Yeah.
is
Yeah. Okay.
curving inwards,
Yeah.
and right, the light rays bend
Then,
outwards.
yeah, that's what I meant. Okay.
Now what's happening over here, remember we talked about virtual images and everything. So
Yeah.
what's happening over here is that the light is diverging, right? So it's spreading out. Light bends outward, it spreads. But what also happens, as we just talked about, that when light passes through glass, there is some low level reflection happening, right? And so what's happening, if you take these refracted lines and you go back, and so you get a point on the same side of the lens where they are converging. Okay.
Yeah.
So this is something that happens with concave or diverging lenses, and this is right what leads to the formation of a virtual image. So you get virtual images with mirrors, you get virtual images with diverging lenses, right? In this case, right, this is a real focus and you get a real image. So far so good.
Yes.
Yeah.
Okay, now certain features. So the center of the lens is called the optical center. So whether it's convex or concave, center of lens is called the optical center, right? And it is denoted with a capital C. Okay.
Yeah.
Then, right, the line that passes through C, so the basically you could say the ray of light, the line passing through C, right, at right angles to the lens. So at right angle to lens is called the principal axis. Principal, oh sorry, not that principal, principal axis, which is basically this guy, right?
The one in the middle.
Yeah.
Okay.
Okay. Clear?
Mm.
Hmm. Then you have something called the principal focus. So let me go to the next page. So the point on the principal axis to which other parallel light rays either converge or appear to diverge from. So, to which other parallel light rays converge or appear to diverge from. Appear to diverge from. What are they talking about? This point is where I said all these light rays are parallel. The center one is the principal focus. The others are parallel to the principal. Sorry, the principal axis. And so they're parallel, and over here they're converging, right?
Yeah.
In the case of the diverging lens, right, I extrapolated these diverging lines and brought them over here. And so if you take a look at it, it appears that this is the source, this is the object.
This is the principal axis?
The principal axis is the center line, right?
Okay.
And so it appears that the light rays are actually diverging from this point,
Okay.
even though that's not what's happening, but it appears to be that way. Appears, looks like it, right?
Yeah.
So in either case, that is called the principal focus or the focal point. Principal focus or focal point, and it is given with a capital F. So if we go back, and I think this has become rather messy, right? This is the focal point. This is the focal point. Okay.
Yeah.
And then the distance. The distance between the optical center, so that's C, and the principal focus F is called the focal length. Okay.
Yeah.
And that is given with a lowercase f. So again, right, going back to the messy diagram, this distance from here, the center,
That's the uh
focal length.
no, the C is the optical.
This is C, this is F, and the distance between the two is the focal length.
Okay. Okay.
Achha. Now they mention that, right, since light can fall on either side of the lens, there are two principal focuses or two principal foci, right? Since light can fall on either side, or as the book says, on both faces of the lens, right? There are two principal foci, which is basically plural for focus, right? And so basically what they're talking about is this and this, right? Converging lens falling on this side, diverging lens falling on the same side. Okay.
Yeah.
And right, or even in like case of a regular lens, right, it has both because there's some reflection, right? And so right, the focal length is the same in either case, right, depending on the properties of the lens. Clear?
Yes.
Okay, then you are introduced to something called ray diagrams, right? So ray diagrams can be drawn to figure out, where the image will form and how large it will be and how far it will be, so what will the focal length be, etc., etc. So I'll give you the theory of it, and then we'll take a look at some illustrations in the text that will clarify it. Okay.
Okay.
So in ray diagrams, information about images formed by a lens can be obtained by drawing two rays, can be obtained by drawing two of the following rays. Right, and so they've actually given three, so any two of those. The first one is a ray parallel to the principal axis. So it's parallel to the principal axis and it is refracted through the principal focus. The next is possibly, right, a ray through the optical center which is undeviated. So basically means it does not refract, it does not bend. Ray through optical center, right, undeviated. So it's not bending, it's just a straight line going through. And the third possible, so depending on the situation, you could have a ray through the principal focus, which is refracted parallel to the principal axis. So it is refracted parallel. A ray through the principal focus, refracted parallel to the principal axis. Okay, now obviously theoretically this makes no sense to us. So let's look at the images, the illustrations. Here we are. Can you see that?
Yeah.
Yeah.
Okay. So, right, in all these three scenarios, you've got, right, these real images forming, right? And one over here is the object OA. So O is the base and A is the top of the object, and it is placed at twice the focal length away. Right? No, sorry, not focal length, the principal focus, right? So it is F is the principal focus, 2F is twice that length, and it's placed further away. So you've got this ray over here on the top that is hitting the lens. The lens is, right, given by this vertical line, okay, and the C is the optical center. So from the top of the image, right, you have a line going straight parallel to the principal axis, right? So the principal axis is what you would call the x-axis, and the lens itself is what you would call the y-axis, because it kind of looks like a graph. So I'm, using those terms, although in reality it's not the x and y-axis. It's not a graph. So, right,
Yeah.
you've got this line going parallel to the principal axis, hitting the lens, diverging, right, bending through the principal focus, right, going through the principal focus, and you extend it forward. Then you got the other line, which is this one, right, and it is going directly through the optical center, and you extend it forward. You can see it's not bending anyway, and the point where the two of them converge is where the image will form. Now what you notice over here, that the farther away the object is from the lens, the smaller the image is, right? You see the other two, right? This object is placed even further away from twice the principal focus. This one, in the second one, right, is placed on this point where it's twice the principal focus, and then this one is placed between 2F and F. So the closer the object is to the lens, the larger the image is forming, as you can see on the right side. And so the same two lines are being used in all three cases, right? A line parallel to the principal axis going through the lens, refracting through the principal focus, and a line going directly through the optical center, and wherever they're converging, right, you can see that a larger image is forming. And then you've got this scenario, right, where you have perhaps right, the object is either too close, or it is, right, uh, a diverging lens, whatever the case is. So in figure 3.2.39D, the broken rays, right, it's giving you a virtual image, because there's nothing that you can see that they're diverging. These rays they're drawing, it's really close. It's closer to the lens than even the principal focus. So it's really close. And so the way the lines, the rays are going, they cannot converge. As you can see, their directions, right? They're actually diverging. And so you extrapolate, you draw the dotted lines backwards, and then you see, oh, okay, fine. So the image is forming on the same side of the lens. And this is a virtual image, right? So, right, this may happen, for example, in a converging lens as well, right? So in all parts of figure 3.2.39, which includes this one, right, the lens is a converging lens. So the reason why this is happening is because the object is too close. So, right, no image is forming. And so if anything forms, it's virtual, and a virtual image, as we mentioned, cannot be projected onto a screen, right? So you don't really see it happening. Does this make sense? How we are drawing these ray diagrams?
Uh, yeah.
Not really.
Hmm? Aram, not really?
Yeah.
Okay, so what would you like? Would you like me to do that on the whiteboard?
It's fine.
Hmm?
Like, I will watch it after the class ends and read it.
Okay, so right, you can do that. and if it makes sense, well and good. If it doesn't, let me know and we'll go over it again. Right?
Okay.
Obviously, right? So the point over here is obviously not to just brush past, but to clarify. Okay. Then we have magnification, right? So magnification is pretty straightforward. Right? Linear magnification, as it's called, linear magnification is defined as the ratio of image length to object length. Right? And so the formula for that is linear. You simply, put that as an equation. Linear magnification equals to image length over object length, and that basically tells you how big or small the image is as compared to the object, right? Has it been magnified so it's larger? So if this is the object, right, is the image larger or is it smaller? It can go both ways, right? That's what's going to tell you. Or is it the same? So obviously, just telling you that is kind of not very helpful. You will, what you'll get is a question where you have to calculate magnification, right? So that's where it will come in handy. Then we're going to talk about spectacles or eyeglasses. So we know that our eyes develop faults and they're unable to focus on objects properly, and so you need corrective lenses in the form of eyeglasses to help you focus properly, right? And so what the eye has is, right, the lens of the eye is a converging lens, right? And as we just saw in the ray diagram, if you notice that the image that was forming was actually flipped, right? And that's what we expect would happen in the eye as well, right? So why are we able to see everything the right way up? Well, that's because our brain processes it to appear upright. Otherwise, the image forming on the inside the eye is actually upside down. Okay. Now, what happens when, right, a person is short-sighted? So short-sightedness, right? And this is what most people experience, is that they can see nearby objects clearly, but distant objects appear blurred. So nearby objects are clear, distant objects are blurry, right? And what's happening is that the image is forming in front of what's called the retina, right? So the retina is the part of the eye where the image should form. And so in this case, the image is forming in front of retina, right? And the reason for that is either the eyeball has become too long, or the lens cannot be made thinner. So the very interesting part of the lens of the eye is that it's adjustable, right? Its thickness can be changed according to what you're observing, and you know, it's really interesting that if you're looking at various objects, you're able to, I mean, not everything's in focus at the same time, but you are able to look at objects that are close by and that are far away, and so you can just like, right, the magnificence of the, you know, the lens that nature has provided you, right? If you try to do that with any, you know, instruments, you would need multiple lenses, and you know, everything, like very few things will be in focus. Now, saying that the lens cannot be made thin enough actually brings us to a point that, you know, the focal length of a, we talk about focal length, which is the distance between the optical center and the focal principal focus or the focal point. And so, right, lenses that are more curved have a smaller focal length. Lenses that are more curved have smaller focal length, right? So just keep that in mind. And so what's happening with the eye over here is, right, your the rays are coming in. So this is the lens of the eye, and right, let's say this is the eye, not really, but right. And so you've got the light rays coming in, and what's happening is that they should be focusing over here on the retina, right? But that's not happening. What's happening is that they are focusing in front of the retina over here, and that's what's happening with short-sightedness. Okay, and so nearby objects work, but objects that are far away don't, right? They can't focus properly. So what we do with near, like people who are short-sighted or nearsighted, is that they are corrected by using diverging lenses. So spectacles use diverging lenses to focus light onto the retina, right? And so what happens in that case is you've got a diverging lens, right? So the hourglass thing, and then you've got the eye. So the way they make it is that's the, well, no, I think I'll just stick with, you know, this. And so what happens is light rays are coming in, they're diverging. Let me just redraw the one over here. So you've got these light rays coming in, they are diverging, and then they're able to focus properly. Okay, so that is the science behind it. Then you've got the other scenario, which is long-sightedness. So that's, as you can guess, the opposite. Long-sightedness or farsightedness. Right, and so far away objects are clear, whereas nearby ones are blurry. Right, and that's when people get the reading glasses. So it's something that happens at older ages, not necessarily right at younger age. And so what's happening over here is right, the lens is not thick enough to accommodate for the light coming in from nearby objects. And so what happens is, right, when it bends, it sort of, focuses behind the retina, right? And this is from a nearby object, right? So the lens of eye cannot be made thick enough. And so, as you would expect, right, the spectacles that are prescribed use converging lenses. So now you've got one converging lens, right, because the eye cannot make its lens thick enough. And so light rays are coming in, they're converging once, and then they're converging again right onto the retina. Obviously, my illustration is not very proper, but you get the point, hopefully.
Yeah.
Does that make sense?
Yes.
Yes.
Right. Now, I was hoping on covering the next chapter as well, but I guess it will be too much for today. So we'll continue from here tomorrow and carry on, right? So the next topic is dispersion of light, after which we'll start talking about the electromagnetic spectrum. Okay, any questions?
No.
No.
Right, so apparently this part was simpler. The ray diagram might have been a bit confusing, right, as you did mention, but do read it, do look at it, how it's explained, the illustrations in the book. If it makes sense, well and good. If it doesn't, tell me and so we can revisit it. All right, so all right, I'm pretty sure you guys are tired. I am. So yeah, all right, see you guys next time.
Okay. Allah
Allah Hafiz.
Allah Hafiz.